Alright, let's see paragraph 13th and 14th. It's a nice question from thermodynamics. So a cylinder is given where there is a rigid partition, frictionless piston, that means it can move. The upper compartment has 2 moles diatomic at 400 Kelvin, lower one 2 moles monoatomic at 700 Kelvin. All walls are adiabatic, means all are adiabatic except partition. The partition allows slow heat transfer. So question number 13 says, when equilibrium, the final temperature. Now you should see that this part or the process is isochoric, while this, as heat starts flowing from here to here, the piston would start moving, and finally the motion always leads to a constant pressure at this part. So this is isochoric, this is isobaric. So for this it would be N CV is 3R by 2 delta T 700 minus T. That's a heat lost, and the heat gain is N CP, and CP has to be 7R by 2 into T minus of 400. And on solving this, you'll be getting 490 Kelvin. So option number D. Then let's go for question number 14. It says now, if the partition is free to move, the total work done by the gases. Now you would see, if this partition is free to move, then this and this both would be a constant pressure process. So let's find the equilibrium temperature first. For the lower one, it will be N monoatomic, so Cp, now that has to be 5R by 2 into 700 minus T. That's a heat lost by this, and it will gain the heat, and that will be 2, that's diatomic, Cp again 7R by 2 into T minus of 400. This solution gives you temperature as 525 Kelvin. Means finally when they equalize, the temperature is 525. And we need to calculate the work. And when we calculate the work, in this particular situation, what you will get is, to calculate the work, you can go with a very nice technique. You can find the total change in internal energy of this and this. That will be NCV delta T, NCV delta T. And if we consider the whole process, you could see that Q equals to delta U plus W, and if you consider this and this, the heat exchange is 0 and work done would be equals to minus delta U. So with the help of temperature, you will find the change in internal energy, and negative of that would be the work done, and that will again lead to option number D. We'll go to the next comprehension, 15 and 16. Alright, question number 15 and 16 is for a spray, and the piston is being pushed, and correspondingly liquid would be evolving up and they would be sprayed out. The first question is, if the piston is pushed at a speed 5 millimeter per second, this is pushed at 5 millimeter per second, the air comes out of nozzle with the speed. This radius is given, this radius is given. Let's call this as R1, R2. So it's all using principle of continuity. A1 V1 equals to A2 V2. Here's the area, so we can use A1 V1 equals to A2 V2, and that will easily give you option number C. Question number 16. If density of air and liquid is rho A and rho L, the density of air here is rho A, the density of liquid is rho L, then for given piston speed, the rate at which liquid is sprayed will be proportional to. Now the point is, as I push the piston, there would be a pressure difference. I mean, originally here there was P atmospheric, but as the air gushes through this pipe, the pressure here decreases. So due to this difference, delta P is of course 1/2 rho A V A square. The difference in pressure gives half rho A V A square. And velocity of air is constant because it has been said for a given piston speed. Look, here the pressure is almost P atmospheric and here the pressure is P atmospheric. So this pressure in difference is also this pressure difference. So that pressure difference, because the height is very small, will result to half rho L VL square. And you could see that VA is constant, so velocity of liquid would be directly proportional to root rho A by rho L. So we'll see the next paragraph now.